You also have to write an equation. So those of you that just joined us in video land, I'm recording the calc help session on Friday. We've already talked about the difference in opposition related rates, and so you're kind of coming in mid-sentence here, but here we go. So with related rates, once we recognize that it's give us some rates and it asks you to find another rate. So then we try to write an equation. Now, what kind of equation though? Obviously we try to write an equation, but what kind of equation? Well, every time we write the same type of equation. What does the equation have to do for us? Let me put it that way.
Equation has to relate one rate to another.
So I need to write an equation. Now, in optimization problems, there's only one equation I can write. I have to write an equation for the thing that I'm trying to make bigger or smaller, right? I don't have any choice. That's what it has to be. For related rates, I can write any equation I want as long as it relates the rate that I know to the rate that I don't know. And sometimes there may be more than one equation that'll do that. There's some problems, I can think of a problem right now that you could write 3 different equations that will relate the rates. No, 3 different equations, 2 of them will relate them and 1 of them won't. It brings in other stuff. But so you can write any equation you want as long as when you take the derivative of that equation, it relates the rate I know to the rate that I don't know. That's what I'm looking for. So write an equation, and I'll just put it simply here, that relates the rates. You all know what I mean by that, right? So in optimization problems, we write an equation for the thing I'm trying to optimize, and for a related rates problem, I write an equation that relates the rates that I know with the rate that I don't know. Okay? Notice all these steps are very similar, right? First step, you look for something specific in the problem. Second step, you write an equation, the right equation. Third step, sometimes we have to fix the equation. Yes? You don't know what I mean by that?
Take the constraining factor, so it's...
Yeah, that's right. Build in the constraints, or make sure that there's not too many variables, or something might be wrong with it that I have to fix. And usually that drives me back to the problem that I have to read a little bit more, pull some more information out to fix whatever's wrong with it. Now sometimes the first time you write the equation, it's perfect. There's nothing to do with it. You just skip over step 3. But often you're going to have to fix it, right? Well, in the related rates questions, why would I have to fix that equation? Because we can have more than one variable there, right? I mean, more than 2.
Because it depends on what we know.
Yeah, exactly. We have to go back and look at the known material, and if I don't have a rate, if I don't know the rate of change for height, then I don't want height in my equation. I have to get rid of it because I won't be able to do it. If I take the derivative and it produces a dh dt, and I don't know what dh dt is, then can't do it. So we did one problem at the very end where I said, remember, I think actually Brennan suggested that you can switch out the h because we knew that relationship between h and r. So we can take all the h's and turn them into r's, or take all the r's and turn them into h's, or whatever, based on their relationship with each other.
I mean, in that regard, it's the same thing, right? Because we just have to eliminate variables.
Right. So the idea is, the difference is, with optimization, we can always only handle 2 variables. With related rates, we can handle more variables as long as we have the rates for all of them. As long as we have the information for all of them, I mean, not just the rates, but we have to know the h and the r, and the drt, dt, and the dh, I mean, I have to know their rates and their values, So then once I fix the equation, then the next step is take the derivative. And that's the same for both, right? Okay. And this is where they part again. So in the optimization question, when I take the derivative, what do? Set derivative equal to 0. And solve. right? What do I do in the related rates question? Yeah. Plug in what I know. And simplify, really. But yeah, solve if there's the letters. I'll say that. Solve. And solve for the missing rate. Because that's what we're usually looking for, is a rate, right? And that's it. That's just 5 steps for each word problem. Read the question intelligently, looking for something. Like, read the question with a narrow focus. I'm not just let all the words that don't mean anything bounce off you. Just look for that one thing that you're looking for, or maybe 2 things, looking for the optimization word or looking for the rates that you know and don't know, right? Once you clue in which one it is, then you can go down the right path. Then you write, if it's optimization, you write the equation for the thing you're trying to optimize. If it's related rates, you write an equation that relates the rates. And the names of the problems help you remember what you're supposed to do, right? That's kind of nice. Okay, so that's a quick summary. And you're right, the statement you guys made at the beginning, that the hard part is I just read the problem and it's just a bunch of words and I don't know what to do. So what I'm trying to do here is give you a more specific, this is what you do. No matter what the words say, this is what you do. And so you want to come in, you don't want to come into a problem with, well, let's see what happens. You want to come in with a problem with a very determined, focused, I'm looking for the right word. And when I find it, then I start moving down those steps. Boom, 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 boom. So that way you're not sitting there reading all the words and going, all right, now what do I do? No. You want to come in with a plan of attack, sort of, okay? Otherwise, the problem will eat you up. You know what I mean? Okay, so let's grab a problem and do what we can. Let's do one that's not too overwhelming right now. Okay, so let's pretend we don't know which worksheet this is on. So we don't have any clue what kind of a problem it is, right? So just start reading it silently, and if you find something that clues you in, tell us all. What clues you in is the related rate? How fast? Okay, so the question is, how fast is the water level dropping? That's a rate question, right? What else? Are we given any rates? It actually says the word rate, doesn't it? So we're given a rate and we're asked to find a rate. That's a related rate, right? And that's obviously related rates. Okay, so now I've recognized it's a related rates problem. So what's my next step? Write an equation that relates the rate that I know with the rate that I don't know. Okay, so let's make sure we know what these things are. Okay, so now we're going to go back and read this. A conical cup. That means a cone-shaped cup, right? It's 4 centimeters across and 6 centimeters deep. That doesn't really help me right now. Water leaks out of the bottom at a rate of, okay. Now this one's a little bit, I have to do some sleuthing here. What is that? It's definitely a rate, but it's a rate of what? What's changing there? Water level. The water level is changing, but it's not changing at 2 cubic centimeters per minute, right? What is 2 cubic centimeters per minute? That's the change of what? Change of volume. How do we know it's change of volume? Well, either you think the water falling out is just pure volume, right? That's the change of volume. Does it affect the change in the radius? Yes. Does it affect the change in the depth? Yes. Does it affect the change of the surface area that's exposed to the air? Yes. But what is it directly? It's just volume falling out, right? Does that make sense? I'm just losing water. I'm not having little pieces of pipe fall out. I'm losing water. That's volume, right? Now, even if you don't get that, what does that tell you? Yeah, it's got to be volume, right? Cubic centimeters, it's got to be volume. You don't lose height like cubic centimeters per minute. or radius by cubic centimeters per minute. So this is telling me that the dV dt is 2 cubic centimeters per minute. Okay? And this is where, this is all part of writing the equation. I think I probably should put a step in there before the equation in this one. It's really helpful to kind of define all your variables. You're not really defining them, they're already kind of defined in the problem, so you're really just kind of pulling them out and just giving them like calculus notation names is all you're doing. Does that make sense? That way it makes it clear what equation we need to write. Okay?
Wouldn't it be a negative too?
Yes, it's leaking out the bottom. Thank you. That would be a negative 2. Okay. Okay, so now, the next thing I usually do is draw my ice box. Because I need to, as I'm assigning these variables, I need to find what goes in the ice box and what goes out of the ice box. Like, for example, that 4 centimeters across and 6 centimeters deep. Where does that go? Is that a question or is that a statement? Okay. You guys agree or disagree with them? Where do the 4 centimeters and the 6 centimeters go? Are those things always true? Okay, they're always true, so we don't put them in the icebox. But what are they? Yeah, they're the dimensions of the conical cup. They're not the dimensions of the water, right? So they're not really even helpful unless we need them. You see what I'm saying? And this is the problem with word problems. They throw a lot of stuff at you might not even need, or you might need it at a certain time, but you don't need it all the time. You know what I'm saying? So you got to be careful about that. This is just telling you the shape of the cone. What happens to the water as it drains out? Does it always stay at a radius of 4? No, as it sinks down, the radius is shrinking, right? Does it always stay at a depth of 6? No, as it shrinks down, so the 4 and the 6 stay all the time, but that's not we're not describing the water there. We're just describing the shape of the thing the water's in. You with me? So it might not be useful to us. We'll have to set it aside for that. Let's read on. Water leaks up the water level. How fast is the water level dropping? That's a question. What is the question? What am I asking there? How fast is the water level dropping?
Water level.
Yeah, but I mean in terms of notation, what is that asking? D what? D what? Well, maybe we need to assign it D. You want to call it D for depth? We don't have a variable for it yet, right?
Would be the change in height over time?
Okay, we can call it height. I'm down with that. So we'll say dH dt, and we're putting it inside the ice box because it says, how fast is the water level dropping when? It's not saying, what is the constant rate of water level dropping? It says, what is the water level, how fast is the water level dropping when, and when what? What follows the when? When the height is 3 centimeters. And notice that goes inside the box too because it followed the when, right? Okay, so what do we need? What kind of equation do we need here? What do we want to relate? Height of the water with the volume of the water. That's what we want to relate, right? You all see that? I mean, again, it's that simple. I know the rate of change of volume, and I want to know the rate of change of height, so that means I need to relate volume and height. That's as simple as it gets. It's not any more complicated than that. Now, the hard part is coming up with the equation that does that, right? I mean, but in this case, it's not bad. I think volume of a cone probably involves height, doesn't it? So if we just knew the volume of a cone, I would do it, wouldn't it? All right. Let's see if we can remember the volume of a cone. Does anyone remember the volume of a cone? Someone here has to remember that.
1/3 IR.
Times height. That's exactly right. Yeah. Remember the volume of a cylinder is pi r squared times height? And a cone is always the third of the volume of the cylinder. Now, you do not have to memorize all the past volume formulas and all that kind of stuff. I will give you any of that stuff you need on a test. So don't worry about, oh no, I've got to go back and look up all the volume of sphere and volume of cone and volume of cylinder volume. No. I will give that to you. That's not something that I expect you to have memorized, okay? Although I don't mind having you think about it right now. Just that when push comes to shove on a test, I'm not going to make you have a big list of them memorized. I'll either give you a formula sheet or just stick it in the problem. You know, like this. If it's in the test, it might be a little note in the bottom. By the way, the volume of a cone is, and the surface area of a cone is, and you know. So, okay. Now, do we have any problems with this equation? We wrote an equation. It relates H to V. Is there any problems?
Yeah.
What's the problem?
We have the dimensions for the total volume, but we want it at a certain amount. Right?
Well, no, that's not a problem. We'll take the derivative later and plug this stuff in, right? Taking the derivative takes care of that. So what's the problem? Can I take the derivative right now? Why not? Correlate number 0. There's an R and H in there. I got variables. What's the problem? I have 3 variables. Now, in related rate problems, that's not a problem as long as I know all those variables, right? So I have 3 variables in there. Do I know what H is at the certain time that I'm interested in?
Yes.
Yes, so that's good. Do I know what R is at the certain time that I'm interested in? No. Do I know what dRdt is? No. So R is a problem. I don't want R in my equation. Right? Do you see that? I mean, I could go ahead and take the derivative now, but that's going to produce there's still going to be an R in there and a dRdt, and I don't know what R is, and I don't know what dRdt is. So I won't be able to plug in enough information to solve for dHdt. Are you with me? So I've got to get rid of the R. So is there anything in the problem that tells me how to get rid of the R? You guys made a statement. You bring this on yourself. You made the statement to come in. Yeah, once you say how to do it, it's easy. I see it. So I'm not saying how to do it. I'm letting you look at this and see if you can come up how to do it. Is there anything in the equation or in the words that tell me the relationship between R and H or R and V or something so I can get rid of the R? Does that do it? What does the 4 and the 6 tell me? That's the depth and that's the height and the radius at the very beginning, right? It says that this is 4 and this is 6. Did I get this right? I get it reversed.
No, the radius is 2.
Oh, 4 across, all the way across. So we're interested in radius, so we'll put a 2 there, yeah? So the ratio of radius to height is 2 to 6. Is that ratio going to stay put no matter where the water is? Like if I went here and drew a little circle down here, would this radius and that height not be the same, but it would be in the same ratio? Yeah, it would, wouldn't it? So what this is telling me is that the ratio of radius to height is always 2 to 6, aka 1/3, right? So if I want to know what R is, so R over H is equal to 1/3, that means that 3R is equal to H, right? Or R is equal to H over 3, whichever one I want to get rid of, right? So that gives me, that's why they told me the 4 and the 6 at the beginning. I don't really care what the dimensions of the Conar, because it doesn't really help me at the time when they said when when H is 3, so that doesn't help me, except for what it does do for me is it allows me to get rid of the R, because I don't know what the R is. Or, it would, I actually do know what the R is now, don't I? But I don't know what the RDT is, though. So I still need to get rid of the R. Okay? Because from this relationship, I could find out the R if I wanted to, but that's not going to help me in this situation because I still don't know what the RDT is. Right? Remember, I have to get rid of anything that I don't know from the equation. Okay. So, how can I fix this to get rid of the R? I'm just going to replace the R with what? V equals 1/3. I'm going to turn that into pi thirds because that's just the number, right? And what do I replace R with? H/3. I put an R up there. I said R when I was writing the 2, and I put a... Okay? So now, do we have an equation with just H and V in it? So when we take the derivative, we'll have a dv dt and a dh dt and an h. All right, let's do it. So that would be dv dt is equal to, oh wait a minute, let's fix this up a little bit. This would be what, pi over 27 h cubed. So then that would be, if I take the derivative of that, that would be pi over 9 h squared dh dt. So we finally completed step 2. Now what's step 2 in a related rates problem? H squared times h. You don't see the h squared? That's because I didn't have my basic one. That's the problem. H squared times h. H cubed. No, that h is 1 by h. That's an h. Remember, we replaced r with h/3. So then we squared it, we got h squared. H squared times h cubed. Square root of 3, got 9. 9 times 3 is 27. And then that's 5. So. Obviously, no calculus is out. Then the derivative, we got that. You all good now? So, can we plug stuff in? Yes, let's do it. So I'm going to replace dv dt with a -2 cubic centimeters per minute. And pi over 9 will just stay there. H squared, that'd be 9, wouldn't it? Oh, that's nice. The 9s will cancel out. And then dh dt is the thing I'm looking for. Yeah? So the 9s cancel out. So now, this 9 here would be centimeters squared, wouldn't it? So notice when I divide by pi centimeters squared, that'll leave me with just centimeters per minute, which is good because I'm talking about change in height, right? And I would get -2 over pi, and that's equal to dh dt. This is a Cactus Help session. You guys are supposed to be like rambunctious and asking questions and saying stop right there and stuff like that, instead of just staring at the screen. It's not going to be helpful if I just talk to you for an hour and a half. You guys need to tell me what's troubling you.
So a lot of times you're pointing and you're like, oh, look, see that? And I'm like, no.
Well, then say that.
I don't see that. It's not obvious.
I need to say it. You need to say that because I think it is obvious. So you don't tell me it's not obvious, I'm like, what's the problem? What are you not seeing? I mean, you have to keep in mind, I've been looking at these things for 30 years, right? So it's hard for me to say, okay, guys, this is really hard. I'm trying to look in here and find something. I can't, it pops out of me. So I don't know what doesn't pop out of you. So you have to communicate that there. So what is it that's struggling here? All of it. See, now that's not helpful, at least yet, because I know that's not true.
Formulating the equation relating the two rates.
Yeah.
When you said, where's the problem? I'm all like, I don't know. I'm all like, I don't see that there was 3 variables.
How do you not see there's 3 variables?
Because I saw R, and I'm like, oh, R is just 2.
Why is R2?
Because that's the radius. I'm not thinking of it as like the radius at the point of 3. Like, I'm just like, oh, yeah, that's information I already know. So I'm sitting there trying to solve.
You saw this as radius is 2?
Yeah,
That's why you think it's 2? Is that what you thought too?
No, but I just was having a hard time figuring out how we're going from DHDT to DRDT to UEDT, and trying to figure out exactly what I'm looking for at that exact.
Yeah.
And there's just a lot of letters, so I'm just trying to get all organized.
Yeah. So, and it doesn't help that it's in a small space and it's all crowded together. So, yeah. Let's talk about that again from the beginning. Now that you've ran through it once and the shock is hopefully wearing off a little. Let's try it again, the same problem again, and see if it makes more sense this time. It's like the first time someone showed you a layup, you're like going, whoa, how do you do that? At least that was what I did. I was like, whoa, that guy's really coordinated. How does he raise his left knee and his left hand at the same time? That's just like mind-boggling. But then after you try it a couple times, then, it's not as bad as I thought it was. Okay? So, let's take it from the top. A conical cup is 4 centimeters across and 6 centimeters deep. Now, this is really important what you're saying, Eric. You've got to understand, in all of calculus, the difference between a static situation and something that's changing. Right? So when you read this problem, you've got to understand that there's this tank here, and there's this water in there, and what's happening to the water? It's draining out. It's changing. So you should immediately think, okay, what is changing and what isn't changing? You've got to get that clear in your head. Right? So, is this thing right here changing?
Itself or the radius of the water.
This radius right here, is it changing? I'm not down here. This, is that changing?
No.
No, that's always 2. The top of the cone radius is always 2. That's never going to change. The cone isn't shrinking as the water shrinks, right? But I don't care about that. That's not what I'm talking about, right? What is the problem talking about? Volume of water. We're not talking about how big the cone is, or how big the shell is, or how big the container is. We're talking about the volume of water. So the water is draining. So that's the problem with this thing. There's 2 different radiuses. There's the radius of the cone, and there's the changing radius of the water. Right? I'm interested in the changing radius of the water, and the changing height of the water, and the changing volume of the water. Right? That's what I'm interested in. It's related to rate. Something that's changing. I'm interested in the change. Okay? So at the very beginning, I don't know if it was full to begin with. At the very beginning, it was full. Yes? So the radius was 2. But as soon as it started draining out, it immediately wasn't 2 anymore. It started changing, right? Okay. So remember, the related rate problems is really what emphasizes the best feature of calculus, is that calculus is the math of change. I can actually measure change with calculus, instantaneous change. Remember, that's how we began the whole quarter. What is calculus? We move from average rate of change to instantaneous rate of change. That's what makes us calculus. We can account for average rate of change in 3 count. That's not a problem. We don't do it that much, but it's easy, right? But I need calculus to do instantaneous rate of change. I need to know how's it changing now. Only calculus will answer that question. Right? So when I look at this, I'm thinking, what's changing? That's the important thing to zero in on. What's changing? The water. Okay, so when I say my variables are volume of the water, height of the water, and radius of the water. Those are the three variables that we talked about, right? And each one of those have a derivative, possibly. Whoops. Well, they do, because it's changing. dv dt, dh dt, and dr dt, right? So then if you go through the problem and think about it, do we know any of these things? Remember, all of this is of the water, right? Do we know the volume of the water?
No.
Nope. It's changing, right? Do we know the height of the water?
Yes.
Nope. It's changing. Oh, yeah, at the spot. Yes, okay. Gotcha. I'm sorry. Yeah, H is 3, right? Okay, good. But not out here, we don't know it, right? It's changing. See, I'm outside the icebox. Do we know the rate or the radius of the water? It's also changing. And do we know it in here? Right, so we could find the radius in there, couldn't we? When the height is 3, what is the radius? Good. It's 1, right? Because it's 1/3 of 3? Yeah? Okay. What about the dv dt? Do we know that? Yes, that's -2 centimeters cubed per minute. What about dh dt? Do we know that? Nope. What about dr dt? Do we know that? Nope. Which one am I looking for? dh dt. So I'll put that in there. So it's okay that I don't know that, right? Because that's what I'm looking for. Yeah? Okay, so now when I write that equation, volume is equal 1/3 pi r squared times height. Now do you see why the r is a problem? Because I see that big question mark right there. That's why having an r in my equation is a problem. Because I don't know the RT. Okay, I know r. I know h. I don't know the ht, but that's fine. That's what I'm looking for. I know dv dt, but I don't know the RT. So I cannot, if I take the derivative right now, it's going to produce the RT, and I won't be able to solve my question. I won't be able to finish it. I won't be able to solve for the ht. Because I'll have 2 unknowns, and I can't solve the question with 2 unknowns. Okay? Okay. Let's do another one. This one will be similar. So in theory, it should be easier to see. You like doing that? Wait, why are you saying enter? What in the world? What am I doing wrong here? There we go. Okay. Air is escaping from a spherical balloon at the rate of 2 cubic centimeters per minute. How fast is the surface area shrinking when the radius is 1 centimeter? What? Is that a related rate problem or an optimization problem? Sounds like it's a related rates, isn't it? There's no biggest surface area or smallest surface area or biggest radius or smallest radius. It's just talking about some rates. Yeah? So let's gather our variables together. So we know what we need to relate. Yeah? Air is escaping from a spherical balloon. So when an air is escaping from a cylindrical balloon, what's going on there? We got volume, right? We got radius, yeah? What else we got? Surface area, we'll just call it S. Anything else? Spheres are nice because all they have is 2 dimensions, right? They either have a volume and R, or volume and a radius, or a surface area and radius. There's nothing else. There's no heights or widths or any of that kind of stuff, right? Okay, so of those variables, which ones do we care about? And keep in mind that means we have a dv dt, a dr dt, and a ds dt, right? Okay. So which ones do we care about? The surface area and radius. That's what we care about, right? Why do we care about surface area? That's what the question's asking. And why do I care about the radius?
That's our snapshot. That's what.
Okay, we know the radius at a certain point. Good. So what is that 2 cubic centimeters per minute then? Oh, whoops. So we care about dv dt too also, don't we? Okay, so we know dv dt is negative 2 cubic centimeters. Why is everything always 2 cubic centimeters? That's kind of weird. Okay, and do we know what dr dt is? Nope. That's a problem. Do we know what ds dt is? Nope, but that's not a problem because we're looking for it, right? Okay. Do we know what the volume is? Well, it's changing. The radius is changing, and the surface area is changing, right? So, but over here in the ice box, the only thing we have is this ds dt, right? That's what I want to know, but I don't. Oh no, and we have the radius, don't we? Radius is 1, yeah. So we want to know what the surface area is what rate the surface area is changing at when the radius is 1. Okay? So let's write an equation. Anyone got an equation for me? Anyone remember the surface area equation from yesterday for a sphere?
1/4.
That's the volume equation. I'll take that. Okay. We got a volume equation that's volume equals 4/3 pi r cubed, right? But that one's not that helpful for us, is it? Because it doesn't have a surface area, right? How about surface area of a sphere? That's 4 pi r squared. Okay? Now, will one of those do? Say something even if it's wrong. Will one of those do? Which one? The surface area equation will do? Good, okay. Why do you say it works?
It's not equal surface area. The thing about me is we don't actually tell me that I want a initial start.
Yeah, we don't care about that. We just want to know the end result, right? We want to know what's happening when the radius is 1. That's what we want, right? Okay? So, we zeroed in on the surface area equation. Why? Because we're looking for the rate of change of surface area. That makes sense to everyone? It doesn't make sense to you, Eric?
I don't know, I guess my brain always tackles these problems by working them backwards. So I'll look at it and be like, okay, I'm looking for the rate of change of the surface area over time. What 2 variables are going to give me that problem?
Yeah.
And then try and figure out, how do I figure out those 2 variables?
Okay.
And you're coming at it from the front where you're like, okay, what's the variable of this, what's the variable of that, and how can I put them together? I guess I'm just doing it backwards, I guess.
Well, do it backwards and tell me whether surface area equation works or not. I don't understand understand what you're saying is backwards from what I'm doing, but that doesn't matter. However you're doing it, does the sinusoidal equation work? What do you think, Andy?
Yeah, I think it works
So if I take the derivative of that, I'll get ds dt, right? And that's good. That's what I'm looking for. What else will I have? What other variables will I have? Oh, let's just do it. Ah, that's a problem, isn't it?
Yeah. We have the radius, but how does that relate to?
Sometimes you just got to roll your sleeves up and check it out, right? Yeah. Roll the sleeves up, take the derivative, what happens? Perfect. We get a ds dt. We're looking for that. We get an r. No problem. I got the 1. Uh-oh. That's a problem. We don't know what the RT is. Right? Okay. So can we find the RT? What? Well, that's if I want to solve the equation, yeah. So they better be a way to do it. How can I find the RT? Is there anything on that board that we come up with that could help us find the RT? Yeah, we know the radius is 1. That's true. What if we take the derivative of that equation? We get dv dt is equal to 4 pi r squared dr dt, wouldn't we? Did that help? So we know dv dt, we can plug in there. We know 1 for r. So could we find dr dt over here? Yeah, so we could use this equation to find the RT, plug it back in there, and then we can answer that question. Yeah, that works. Okay. There's probably a cleaner way to do this, but I was just doing what you guys told me. I noticed I didn't get any input on it. I just asked questions. Of course, that was all of you working together. But between the 4 of you, you came up with some questions, you came up with some answers that led us to that. Yeah? Now, what we could have possibly messed around with these 2 equations earlier and just got rid of the r. You kind of see that? I could solve for r, for r and then replace it with a v or something like that. They only do once, but this works. I mean, it doesn't matter. I just had the two related rate questions, right? I have to solve this one to find the RT, then I plug it back in there. Because really all I need is to find that, right? So as I think Eli led us on this one, he said, let's just take the derivative and see what happens. We got that. Oh, that looks good. I need that. I got that. We discovered we didn't have that, so then we had to go back and find a way to get it. That's all. Right? And really the problem with these questions is, and I don't mean to insult anyone, you guys are just not very, your mathematical perseverance is not very strong. And it's not you, it's just everyone that gets to the calculus level. I mean, you haven't had to work that hard at math. And now you might disagree with me. No, I worked really hard at math. Well, yeah, but you haven't really had to work hard, like, at a problem where you say, I don't know how to do this, but I just keep working at it and keep working at it and try new ideas, You have to do it in this class, for sure. So your mathematical perseverance is hopefully growing, right? And I've definitely seen that. And some of you have had you for several quarters, and I've seen your mathematical perseverance grow, right? Now this is a new test one, because this is going to test your perseverance to no end. If you're going to try something, and it'll just go, that didn't work. And if your perseverance is weak, you'll just give up. I'll see that. If your perseverance is strong, you'll say, okay, I ran into a roadblock here. What else could I do? Well, I wrote that other equation up here. I wonder if I can do something with that. It's calculus. I might as well take a derivative, see what happens. I don't know. You got to kind of keep pushing at it and trying it. And what the problem is that sometimes, and I think this is the problem with online homework, is as a lot of you guys, you try once, something makes sense, it doesn't give you the right answer, then you start doing stupid stuff. You just say, oh, I wonder if this would work. Oh, maybe I just put the wrong unit, so I'll throw some different units in. You just start trying stuff that you know doesn't make sense. And that really hurts your mathematical perseverance, because you try something and you think you're persevering, you're trying new things, you're trying the 35th try on that web word question, and it's still not giving you the right answer, and you're going, see, these answers are stupid, I don't know anything, this is a waste of my time. But that's brought about because you're trying stuff that you know doesn't work anyway. If you thought about it, you know it's really silly to try this. You know what I'm saying? Does anyone know what I'm saying? Have you found yourself doing that?
Yeah.
Just putting in stupid answers that you know aren't really answers? Just because, well, maybe the system's broken. I know this is not the right answer, but I'll just give it to it anyway, because maybe it'll just be happy and it'll give me the green line. That doesn't help. It doesn't help at all. It actually hurts to do that. Because then if you get lucky and it actually takes it, you think, oh, the system's broken, but it took that stupid answer. I don't even think it's right anyway. But then you don't discover that you just had a misunderstanding somewhere or something, you know? Okay, enough lecturing. You guys are here because you're the dedicated ones and care. So, not that everyone that's not here isn't dedicated and cares. I mean, they could have conflicts. I understand that, but.
I was definitely regretting asking you to do this last time. Closing the bar. I was like, I forgot I worked tonight. Why did I do this to myself?
I've got to show up. I asked him to be there.
Exactly. I was like, I don't know if anyone else is going to go. Can't be that guy.
I appreciate that, but I wouldn't hold it against you if you didn't show up, but I appreciate you having that thought, though. Okay, so is there a problem that I could do that maybe one of you is keenly interested in, or?
Real quick, can you go back?
Sure.
Why can we input radius equals 1 into the volume, but not the...
No, I put it in here and here. Not there.
Okay.
You can only put it in after I take. See, I had to take the derivatives first before I can put the one in.
Mm-hmm.
I can't put it in there. I can put it in anywhere after I take the derivative. Right? If there's 3 different equations worked here, I can take the derivative of all 3 of them and plug the one in after I take the derivative and see which one works. You know.
Yeah.
I mean, that's really the method. Sometimes is you find an equation. Take the derivative of it, plug in everything you know, and find out you're missing stuff, like, oh, I guess that was the wrong equation. I'll go try a different equation. Plug everything I know, and like, oh, that one works. Great, I'm glad, you know? I mean, but you cannot open the icebox until you've taken a derivative. That's the key. You got to take the derivative first, then you can take stuff out of the icebox. And sometimes that icebox is packed. You might have 3 or 4 variables in it, you know? But you can't touch it until you take the derivative. Right? Okay. That's a great question, Eli, because that is probably the number one problem on the test is people plug in variables before they take the derivative. And it's always puzzling to me because they'll plug this one in, but they won't plug that one in. And of course so they don't get, so if you plug everything in, you know you've done something wrong because when you take the derivative, you just get zeros everywhere, right? But what happens is people plug this variable in, but they don't plug that variable in. So when they take the derivative, they still get something. So they think they're doing it right, but they're not because they plugged a number into a changing variable that's not set yet. I can't put it in until after taking the derivative. So that's a really big key. Okay. So is there one that's maybe you've seen on, and it could be optimization related rates. We don't have to do more related rates. I want to do whatever you got is helpful because this is your help session, right?
Optimization is a lot easier than related rates.
That's good. That's because we've been working at it longer, right? This will become easy too one day, right? Okay, someone have one for me? I can do more, but I want to do one that someone's keenly interested in.
The first one on that first optimization worksheet you gave us, with y equals square root of x.
The nearest distance one?
Yeah.
Yeah, that's a fun one.
It's not something I remember.
Yeah.
Okay, I was wondering.
Can you remind? Can you remind me what it is? It's the closest point to what?
Yeah, find the point where it's nearest 4, 0.
Right? It's on that y equals square root of x. Did I remember that correctly?
Yeah.
Okay. So in this case, I know it's optimization, so I'm trying to minimize. And what am I trying to minimize? What does nearest mean? Yeah, so 1, 2, 3, 4. So there's some point on here, I don't know where it is, that makes this distance short. Right? That's what I want. I want to minimize that distance. Okay? And yes, there is a distance formula that says, it's used the Pythagorean theorem actually. If you draw a little right triangle, you'll be able to see the two things. It's x minus x squared plus y minus y squared, where it's y1 and y2, all that kind of stuff. But so basically, I just take 2 points and I subtract the x coordinates from each other and square it, subtract the y coordinates from each other, square it, and then square root it. That's the distance formula. Okay? So what are my 2 points that I'm taking, that finding the distance to? Well, one of the points is 4, 0, right? What's the other point? We don't know. So let's assign it a variable. Which variable do you want to assign it? Well, since we're on the xy plane, you might as well use x and y, yes? So let's use x, but I don't want to use y because that brings in another variable. What could I do for the y? No, I want to use an actual x, not a new variable, right? Ah, there we go. So just call that square root of x. Yeah? So then I just plug into my distance formula. What? X minus 4 squared plus square root of x minus 0 squared. So maybe we'll simplify this a little bit. Oh, and x. How about x squared minus 8x plus 16 plus x. So then I just have to take the derivative of this baby, don't I? So the derivative of that would be 1/2 times x squared minus 7x plus 16 to the negative 1/2 times 2x minus 7.
Also, on the video I watched, because it's a square root function and you're looking for the smallest number, you can actually just ignore the square root because the smaller the inside gets, the smaller the...
Yeah, that's true.
So you can actually just get having to use the table and
so you really, and you can see right now that's true also because I'm just trying to make the top 0, right? And all this stuff's on the bottom. So really I'm just trying to set that equal to 0. Yep. 2x minus 7 equals 0. That means x is equal to 7/2. So that means the point I'm looking for is 7/2, comma, square root of 7/2. Because x is the x part of that point. I think another problem that some of you have is you're just too intelligent. And you start looking at these problems and try to solve them without calculus in your brain. And that's almost a detriment in this situation because there's a good chance you won't be able to do that. But even if you do it, that's not what we're looking for in here anyway, right? And it clouds, it gets in the way of your thinking. So, like I said, you want to come to the problem with a very narrow-minded, kind of focused look that I'm looking for to solve. I'm trying to optimize this problem. So all I'm looking for is to find something that I'm trying to, in this case, minimize. So I need to write an equation for the thing that I'm trying to minimize. Take the derivative, so I'm almost like detaching myself from the problem sort of. I'm just going to the problem occasionally to grab something. I go in and say, okay, smallest distance, okay, this is formula. Okay. This is formula from what to what? 4, 0, and x comes sort of x, okay. I just kind of keep ignoring the problem. I just go there to get what I want. You know, to fit my 5-part plan or whatever. Recognize it, what's I'm trying to optimize, equation for it, get rid of that, and plan. I don't want anyone to distract me from it. Okay. How about another one that someone's would really like to see done or just like to do?
I've got a homework problem that.
Sweet. Yeah.
It's an optimization problem. It says you're trying to build a rectangular garden. One side is a brick wall costing $20 per foot. The other 3 sides by a metal fence costing $10 a foot. And the area of the garden is 22 square. Trying to minimize the cost.
Minimize costs. Yeah? So that means we need to write a cost equation. In order to write an equation, I probably need some variables. I'm open to suggestions. F and B for fence and brick. Yeah, I mean that's fine because it just reminds me this is the link that has a brick in it, but you don't want to confuse yourself into thinking that that's brick and that's brick, right? So this is a problem with when you're assigning a variable. You want to be clear on what your variable is. Usually we just throw a variable on a picture, and later, again, this is a problem that I see a lot. People do just this, and then later they replace the B with 20. See why that's a problem? Or see the confusion they have there? They weren't clear what their B meant, right? When I stick a B there, what do I really mean the B is? The length, right? How long that rectangle is. Which is how long the wall is too, but it's also how long this side down here is, right? So I need to make sure I'm clear on what my variable is doing. It can't be the price of the wall and the length of the wall at the same time, right? So if you need to, make a little, actually maybe not even mental note, maybe even a physical note, like B, length, F, width of the rectangle, right? That way I know what it means, yeah? So then when I go to write the cost equation, how much does it cost to build this rectangular wall, a rectangular garden? Well, it's going to cost 20B for sure, plus 10B. So that takes care of that part and that part, right? What else? Plus 20F, because that would be a 10F and a 10F, right? So my cost equation is just 30B plus 20F. And I'd really like to take the derivative right now, but I realize I'm in an optimization problem, so I can't take the derivative. Why can't I take the derivative? I have too many variables, right? So I got to get rid of one of these variables. Is there any information that he told us that would help us get rid of a variable? The area. Oh, because area, in terms of our variables, is BF. BFF. And also area is 22, so that means 22 is equal to BF. So 22 divided by F is equal to B. So then I can come back to my cost equation. Now I'm fixing it. This is step 3, right? I'm fixing my cost equation. So that would be 30 times 22 over F plus 20F. What's that? 66. F to the negative 1 plus 20F. So then if I take the derivative, whoops, c prime is equal to negative 660f to the negative 2 plus 20. And I want to set that equal to 0 because that's what I do in optimization problems. So then I get negative 66, or 660 is equal to negative 20f squared. Divide both sides by 20, and I get 33 is equal to f squared. So I'd have to square root 33. And of course I get a plus or minus, but the plus doesn't make any, or the minus doesn't make any sense. So the length of that, wait, that's f, right? Oh, so the width of the thing is square root of 33. And I could find the other one by dividing that into 22. Camden, you got a question for me? Okay. Oh, what?
The f to the negative 2?
Yeah.
How did they end up on the other side of the positive?
Multiply both sides by x. F is f squared.
So negative 660 f to the negative 2 is like negative 660 over f squared.
Equals one.
Yeah, and multiply both sides by x squared. Get rid of the f squared on top.
I did a couple steps there in my head.
More questions? Comments? Concerns? Number 7 off of homework 10. That sounds fun. Do you have it there? Oil spilled from a ruptured tanker. Oh. Spreads in a circle whose area increases at a constant rate of 5.5 miles squared per hour. How rapidly is the radius of the spill increasing when the area is 9 miles squared? Is that a related rate problem or optimization problem? Yeah, because it talks about a rate and that's for a rate, right? Okay, let me put this up here so everyone can see it.